Welcome to our NeuroNexus webinar series. We run this every Thursday. We haven't been running the 2 o'clock. This is only our second or third 2 o'clock show. Next week, we're going to do something a little different. We're going to have one of our engineers come on, Peter Garreau. He's going to talk about custom chambers. So if you've ever thought to yourself, you know, how can I make the implanting easier, more robust, or more consistent results? The custom chamber with a drive inside is a great way to go. You could even have it add a cap to it for your chronic so the animal can move around and all the components can stay safe inside there. He's going to talk about that. There's also a lightweight option for small animals, and then, you know, a titanium, good substantial one for large animals. So with that, I'm gonna hand it over to Alexis.
Hi everyone, thanks for joining us. So today's topic is NeuroNexus Insider. And today's insights that I wanted to give, first of all, I should introduce myself. I'm an application scientist at NeuroNexus. I've been with NeuroNexus for 2.5 years, and I still am an electrophysiologist. So I have your perspective on this technology. I know there's a lot to learn and a lot to digest. So I wanted to walk through what makes the NeuroNexus probe. And my goals for today is, one, to get you a little bit more familiar with NeuroNexus in general, learn to navigate some of the information that's in our catalog, and then really understand the language of selecting a probe. So the different specifications that you can include when requesting or designing one. And along the way, I'll offer some tips so that you can really refine the probe that will best suit your experiment. The way that I wanted to introduce NeuroNexus, since I'm going to be talking a lot about numbers and model numbers, so not all numbers, some letters too, is by numbers. So NeuroNexus has been a company for 16 years out of the University of Michigan, making silicon probes on silicon wafers. There's a combined couple hundred years of experience, I believe, at this point. And the technology is ever evolving. Our devices have been in use in over 950 institutions around the world. That's over 50 different countries. So here's a map if you wanted to try to wave up at the satellites and see if you're on this map somewhere. And the best stat that I like to tout is that we have nearly 300 Nature papers that cite NeuroNexus products in them. Another number that maybe I don't tout as often is that we currently have 200 numbered pages in our catalog. So the catalog can be found on the NeuroNexus website, neuronexus.com. If you go to the products menu, all the way at the bottom, there are catalogs and brochures. And the 2020 catalog can be found.
You're not sharing the
I didn't.
No, we're still looking at the PowerPoint.
Okay, I'll show you my whole screen because I don't mind sharing everything I'm doing. Okay. Are we good now?
Yes, sorry.
Thank you. Okay. So I'll go back then. Let's just go back to neuronexus.com. The catalogs and brochures menu under products, the 2020 catalog is here. And it's a big file. I had it all open. Oh, I was going to say I have a PDF open as well, but I wanted to show you that it's really there at the link that I will put in the chat in a moment. Okay, so in this index, which is currently on page 5, we've broken out very comprehensively the different product categories, sort of an orienting of where you can find some things, subcategories as well. One that I like to use is the ECOG subcategory, where you can click right to that heading and get some, key features of the product, some material specifications of the product. And I'm going to jump back to the top really quick. That's the fastest way. And what I want to focus on here the most, so this is a really large group of pages, all that fall under the A-style probe designs. And you'll see some familiar images here. This is a 16-channel probe. And that's where this design starts. This section of the catalog starts. And I wanted to just give a quick tip. Actually, I'll go back to the presentation. The first tip was what I just showed you. You can use that index and click to different section titles so that you can get quickly to wherever you're interested in browsing. And I also wanted to mention that the probe designs are organized, and some people may never figure this out, so I wanted to just let you know right away. First, they're organized by channel count, so there's 16 channel probes, then 32 channel probes, then 64 channel probes. Then they are organized by length. So as you saw, there was a 3 millimeter long 16 channel probe. And then they're organized by number of shanks. So we're going to have a single shank 16 channel probe that's 3 millimeters long, and then a multi-shank 16 channel probe that's 3 millimeters long. And then we'll get to a 16 channel probe that's 5 millimeters long. So that's how the organization follows. So one other number, I'm already starting to rattle off different specifications within these model numbers, is that there are actually up to 9 different pieces of information within a big probe model number. So here's an average, believe it or not, probe model number, and there are lots of different features. So I wanted to walk through this so that everyone can understand, first of all, the options that are available, but also how best to configure your device. So we'll start with this A at the beginning. That's your probe type. This tells you some broad information about the probe. It does not mean acute in this case. The A is for axial, and so it's a penetrating probe. It can be one dimensional or 2-dimensional. So 1-dimensional, we mean a single shank. It goes along one insertion axis. All the sites are sort of aligned vertically. 2-dimensional means a multi-shank probe. It covers a plane of recording span. And there are other probe type options you may see in the catalog. So penetrating probes could also start with a V. That's the vector array, the typically primate array that'll achieve really deep recordings. The M is for probe designs that are built into the matrix array, which is our true 3-dimensional recording array. And Q would stand for Qtrodes, which are our low-cost 4-channel probes. Those are great for training, practicing your recording setup, handling silicon probes for the first time. C is for cardiac grids, as well as for nerve cuffs. So these are now flexible arrays instead of the penetrating arrays. And then E is our other surface arrays, and the E stands for ECOG and EEG, but it also encompasses some others. Then there are some probe model numbers that don't fall into this scheme, and they're usually named for collaborators that have custom designed certain things. Like, for example, there's a wide range of Buzaki style probes in our catalog. So this second piece of information is the first number in the model number, and that represents the number of shanks on the probe. So currently this probe would have 4. Currently in our catalog, there are designs with 1 to 16 shanks. So here's an example single shank probe. There's 1 electrode track, so it's a great transition if you're used to using like single tungsten electrodes, and the mechanics of inserting this guy would be very similar, but you now have recording sites at many depths, so you don't have to move the probe as much to cover a wide range of a target of interest. The 16-channel probe would look like this. What you get are multiple insertion locations, and this was developed by Lisette de la Prida for an in vitro application where she needed in her slice or her culture that many sites in a very small range of depth. And so anything in between, of course, is a possibility. And I'll show you how to request a custom design at the end. What also just wanted to kind of give my science perspective is that this multi-shank probe offers you the ability to extend your recording span along, say, the medial lateral axis or the anterior posterior axis. So you don't have to make multiple penetrations with a single shank probe. You can make them at once with one insertion of the probe. And if you want to expand your recording in multiple axes at once, you can combine multi-shank probes, 2 to 4 of them, into a platform and create a true 3-dimensional matrix array. So this next number in the model number represents the number of electrode sites on each of the shanks. In this case, there are 16. We have made shanks with a single site, as you saw on the Prida probe, and up to 128 electrode sites on a shank have been fabricated so far. And of course, more electrode sites mean more data. And when you get intimidated, what am I going to do with all this data? How am I even going to record from this many channels at once? The NeuroNexus SmartBox Pro is built to acquire 1,024 channels of data simultaneously. So we've got you covered. Pro tip number 2 is that this multiplication here, 4 times 16, is going to tell you the actual number of electrode sites on your device. It happens to match this 64 over here at the other end, but it doesn't always. So we use 16, 32, or 64 channel connectors. So if your probe has, say, 30 channels in it, like a 5x6 or something, or a 3x10, or whatever you want it to be, you will have some extra pins, and those could be used for breakout wires to record EMG, or tie to a cortical screw for EEG or something like that. So just know that that is also an option. The possibilities are endless. The next term in the model number is your electrode site layout. So this probe happens to be a polytrode, which means multiple columns of sites. In this case, there are 2. And we have several options. So the linear was the probe that I had shown first, where there's a long span of electrode sites. This replicates a single insertion of a single electrode, what we called passage experiments, where you have a single wire tip and pass it through the tissue as you go and record from different depths. This now replaces that by allowing you to record from different depths all at the same time. An edge design is also arranged linearly, but the sites are over at the edge of the probe shank, which some believe allows them to pick up signals from more off to the side of the shank rather than just in front of it. A tetrode, so when we all think of, historically a tetrode is a bundle of 4 wires, it gave new redundancy to your recordings, and was the first sort of triangulation for spike sorting. We can also, NeuroNexus will put multiple tetrodes. You don't just have to have 4, you can have 8, 12, 16, whatever number of sites. So that starts giving, discriminability of your spike waveforms. And then when you start stacking lots of tetrodes together in those columns, like I mentioned, a polytrode gives you linear layout, but also the density and redundancy of a tetrode layout. And of course, these designs can be on multi-shank probes. So you get, like I said, multiple shanks expand your recording span, quote unquote, horizontally within your target. And just pro tip number 3, I showed a multi-shank linear probe, but we can also have multi-shank polytrodes, multi-shank tetrodes, or even 1 shank linear, 1 shank polytrode, whatever the case may be, whatever you need. If you need density in one region and sparse recording in another, that can be done. The next component of the model number is the shank length, and the units are given, so that's self-explanatory. We fabricate probes ranging in length from around 1 millimeter to around 15 millimeters. That's the most typical. But for recordings deeper than 10 millimeters, we do recommend considering the vector array, which I mentioned is the primate, typically used in primates to record very deep. I mean, the longest recording depth that's standard is 110 millimeters, so 11 centimeters deep if needed. One thing that goes hand in hand with the shank length is its thickness. So we have 2 different options. Shorter probes, say 5 to 6 millimeters and shorter, tend to be on a 15, so 1.5 micron thick substrate. And probes 5 to 6 millimeters and longer tend to be on a 50, so 50 micron thick substrate. But here's another tip. If you like to use a probe design that's 3 to 5 millimeters long, say, and that design goes low on stock or goes on to back order, which I know some may be experiencing right now as a lot of facilities are closed and clean rooms are required to make more of these probes, just ask us if maybe that short design is available on the 50 micron thick substrate instead. It may be readily available and you can get your probes very quickly. Okay, the next component of this model number represents the electrode site spacing. So just note, this order is consistent always. I'm not just using this one. This is representative of our model numbers. So we're halfway through. This is the electrode site spacing, which is center to center in microns. So it's not just the gap between the sites. It's the actual center to center distance between sites. So it's more representative of how far apart are my recordings. And in this case, there's a 23S. So on polytrodes, you can see this S sometimes. And the S stands for staggered. When the polytrode is not staggered, the sites are in a square grid, and each side of the square is that spacing apart. So in this case, it's a 50. You can see there's a vertical spacing of 50 shown here and a horizontal spacing of 50 shown here. With the S, your sites are now in a triangular grid. They're staggered from one another. So they're the columns are offset, and you have the triangular grid, and you can see here that there's one side of the triangle is this 25, another side of the triangle is this 25. And so in the probe we're looking at here, it's 23 micron spacing. Again, smaller spacing, higher density of your recording adds redundancy to your recording, which can aid in spike sorting like the original tetrodes did. When you request a custom design, so there's some standard spacings available in the catalog, there's usually a wide range. You would request typically between 20 microns to hundreds of microns in electrode site spacing, and just something to remember and kind of explain why 20 is a small number. You can think of these, again, it's center to center spacing. Our typical sites are a 15 micron diameter circle, and usually we say the empty space where there's no electrode is about 4 microns, and you know they're really, it's tiny, but it's far enough apart that they're not running into each other. So if you add that 15 and that 4, that's 19 microns. So a nice round number, we say, you know, smallest site spacing would be 20 microns. The next part of the model number is the Shank spacing now. So this is the center to center, or you could say tip to tip spacing of the shanks. If the shanks are not the same length, it's hard to imagine the distance between their tips in just like at the same depth. So you can think of it as center to center spacing. And for us, the design space ranges from 50 microns, which is quite small, to nearly 4 millimeters, which is quite large. So the 50 micron spacing is the Pareto probe that I had mentioned before, where each shank only has one channel. So keep that in mind, that the close spacing of shanks is possible when the shanks are very narrow. If the shanks get wider than 50 microns, then 50 micron spacing means you're inserting this solid block into the tissue, which is not ideal. This other example, so this is not in the catalog, this is what it would look like when we render your custom design for you to approve the design. This is a you can see it here actually, 3.82 millimeter spacing between these shanks. And this was produced because the investigator wanted to record, you know, a little bit more superficially on one hemisphere of the brain while simultaneously recording at a deeper structure that was presumably connected on the other side of the brain. And instead of having to implant 2 probes in the same surgery in multiple animals, they made their life a lot easier by just knowing that they could always insert 2 shanks repeatably and simply by just making them both on the same probe. You can also, this facilitates, you have 1 connector to plug in instead of 2, etc. So know that this is probably one of the larger ranges that we would go to, but anything in between, again, is an option. The next number, now we're near the end, the next number is the electrode site surface area. So the units of this are square microns. And I know 177 sounds like a pretty random number, but this is actually our most typical site area. It's good for single unit recordings, also good for LFP recordings. And what it actually is a circle with a diameter of 15 microns. So I mentioned that before, but that's a nice round number. If you see the 703 surface area in our catalog, that's just a circle with a 30 micron diameter. And finally, the last piece of the model number. So normally in the catalog, actually, I'll show you this way. Nope, I won't yet. Okay, let's talk about this probe first. This probe's connector package is the H64LP, which is a hybrid package. It looks like this at the bottom. There's a 30 millimeter cable. That's what the 30 millimeter corresponds to. The H stands for hybrid. So the hybrid means there's this flexible cable as well as the rigid circuit board. It has 64 recording channels. That's the number 64. The LP means low profile. And what the low profile in this context is that there are actually 2 32 channel connectors here, and they're spaced only 2.8 millimeters apart, again, center to center, which makes this package compatible with 64 channel head stages. Note, this is not compatible with 2 separate 32 channel head stages. If you have this on your probe, you do not have room to plug in 2 32 channel head stages. There are lots of other connector options, and this is what I wanted to show. I started to show before. You, first of all, specify your probe design. So you'll see this in the catalog. You won't see this appendage in the catalog, but then you'll see a list of possible connector packages that can be put on this same raw probe. There are lots, so I'm going to just walk through the broad categories here. The A series, so in this case, the A, not like the A that stands for axial at the beginning, but the A on a connector means acute. And these are large, easy to handle circuit boards. They're lower cost, but they are not something that you would implant on an animal. They're long and heavy. Our CM series, so CM16, CM32, these are fixed packages as well. So it's rigid from the probe through the connector, and they are omnetics-based connectors. The H series, as I mentioned for the example probe, is hybrid. So there's a flexible cable between the silicon probe and its connector. Whatever its connector may be would follow that H. And here's another little secret, that there are often two variations of the H package available. One is without a C, where your connector is in the same plane as your probe. And the HC turns the connector so that it's coming out of the plane of the probe. And it just depends on how you prefer to implant your device. If you want to lay this circuit board flat on the head somewhere and have the connector coming out, it's easy. If you prefer to have flexibility in how you angle this connector, then you could just use the regular H package and position your connector any way you wish. This is also compatible with our microdrives. The MR series would be MR compatible. They're nickel free so that you can use them in a magnet and not move the probe, damage the tissue, etc. The O series is the optogenetics enabled package. So these have an O preceding any of the other or many of the other package types. If you expect to have an optical fiber affixed to your probe, you need to have the O on your package. If you don't, we won't put a fiber on it. So double check that. The Q series are the connectors that go with the Qtrodes that I had mentioned before, the 4-channel probes. There are some 4-channel connectors that don't start with Q in the catalog, but they're organized together. The Z series are the ZIF Flip compatible probes. So we collaborated with Tucker Davis Technologies to have our probes interfaceable with their ZIF Flip technology. Then these packages are also in the catalog, but they're not organized by series as much. First are the I, which are the IN10 compatible probes, and these will interface with 1 or 2 128-channel head stage modules from IN10. And the S series, so there's hybrid versions of both of these as well. The S series are our smart probes. So they're S128, S256, H128, and H256. These are the high channel count onboard digitizing probes that look like this and would interface just through a mini HDMI connector to our SmartBox Pro system. And you can record from 4 of these simultaneously. Finally, the D series is probably one of the least common, but if you see a connector package with a D in front of it, that means it is drug delivery compatible. There's a fluid channel affixed and a fluid port on the package. I wanted to give a couple of other examples. So we made it, we did it. That was a run through an average model number. Here are some simpler ones, just so you know that it's not always so complicated, but the more information you can put into this, we find is the most useful. Then you know exactly what the device is going to be. So I don't want to intimidate anybody. Here's an example where there's no, okay, let's make sure we understand. It's an axial array with 1 shank, 16 sites on the shank. It's 5 millimeters long. The sites are spaced 100 microns apart. The site area is 177 square microns, and we have an acute 16-channel package. So we don't have a fancy site layout. That means this is linear. We don't have a shank spacing because there's only 1 shank. So you don't have to leave a blank space or something like that. This would just be interpreted that way. Right, so to reiterate, not all pieces of the model number are always required. So don't worry if you're missing some. And then I wanted to give an example of one of our ECOG grids because the schema is a little bit different. This example is a 32-channel ECOG, so that makes sense. The 300 is the grid spacing on the ECOG, so that's similar, just in a different location. Center to center spacing of a square grid, typically of electrode sites. The cable between the grid and its connector is 20 millimeters long. and the diameter, not the area, the diameter of the electrode sites is 50 microns. And then the package would be the same. It would always be an H because this is a flexible probe that would have a flexible cable. So it's a flexible interface to your H package. And that's just what I said. So the channel count, then the site spacing, then the cable length, then the site diameter. Any of these specifications can be customized. That's the fun thing with NeuroNexus is if you can specify by these pieces of information. So in the lower left of this sheet, we could send this to you if you say, hey, I want to modify something from your catalog or start over completely. Here's why. You can give us some information about you, how soon you need to achieve this amazing science. Describe your experiment a little bit. So I geek out over these all the time. It's like, what a cool idea, and how can we help you? Any constraints you have, hey, my animal's already got 3 head posts and a tiara that he has to wear all the time. So how am I going to fit this probe? You can, first of all, we'll specify, okay, it's the same thing as the model number. You don't have to make up a model number. We can do it for you. Number of channels, shank lengths, number of shanks, shank spacing, minimum shank width, maximum shank width, excuse me. Site area, site material, the substrate material, so penetrating probes is usually silicon. Surface arrays are usually polyimide. One thing that's not included in the model number, but is an option, is whether or not there's an internal reference site on your probes. That's another electrode site that's not counted, but your connectors do often have a reference channel as well, so we can route to that, as well as the regular transmitting channels. The thickness you would tell us, but again, it's not usually mentioned in the model number. The probe package is that last piece, the connector. And we do actually have an option. It's not often exercised, but if you want to be the only person in the world that can ever use this design for at least for a year, so you can stay ahead of the curve, you can actually say, this is mine and only mine. And what we like to say is, if you can draw your design here, we can probably make it, again, within basic geometry constraints and material properties and things like that. But the best thing to say is ask us, propose an idea, just fill out this form and we'll see where it goes.
All right, it looks like that is it. I wanted to remind everyone that next week we're going to be doing, Peter Guerreau is going to give a custom chamber. After that, actually, the June 4th or June 11th, we're going to have a special guest. So look for your emails on Monday about that announcement, and we'll announce that special guest there too. Very exciting. And that's it for us. Thank you very much.
Thanks, everyone.